my presentation is, there we go. My brief this morning is to present you with a flavor of IAMAS achievements over the last century. And to that extent, when I use the acronym IAMAS, I'm having problems here. Let's have a go. Nope. Okay. When I use the acronym IAMAS, I mean not only the International Association for Meteorology and Atmospheric Sciences, but all its previous emendations as well. And if you want a nice, detailed, chronological assessment of those changes and the work that the association has conducted and its commissions, then you can do no better than look at the article of Mike McCracken and Hans Folkert in the special issue that was referred to by Hans earlier on. So I commend that to you. But it leaves me with a possibility of adopting a more broad brush and light touch to the whole subject, and I hope that will be reflected in what comes next. What I want to do is to give you an outline of the nature of the science, then to give you a brief glimpse of the advances that have taken place, and then to pick out some specific examples of distinctive, characteristic IAMAS contributions. So first of all, the nature of the science. It is quintessentially observational. The first president of IAMAS said in 1920, we need data everywhere all the time, and was laughed at, but it actually is true. The science is prediction and outcome orientated, and this gives the researcher a particular mindset that is really useful, because he wants to marry his pure research with the implications of that research. The atmosphere itself is complex and chaotic. The complexity means that there are constraints and limitations on how quickly we can progress. The chaotic element means that there's a limit predictability horizon. And those two things together mean that there's a perception problem for our science, because we are not producing perfect forecasts. And I'll deal in some depth with that later on. It's a public science. The public look at our products day by day, and they're scrutinized by them as well. And then, like some of the other associations, but perhaps particularly true of us, as a non-governmental organization, we exist alongside a very powerful intergovernmental partner organization, the World Meteorological Organization. So our sphere of interest is the same, our mandate is different, we have different budgets, funding sources, and very often we have different objectives. So there's collaboration, competition, and whatever. And maybe I'll touch on some of that. If I move now from the character of the science to the advances, then what I want to do is to give you briefly a quick look at the changes, the massive changes from the few to the multitudinous where observations are concerned. What has happened to prediction, from catastrophic predictions to not predictions of catastrophe, but catastrophic predictions, to skill levels that are eminently revolutionary in their level of achievement. I'll refer to the complex and chaotic nature, and in particular zero in on the perception. And so if I first of all refer you to the observations, basically there weren't that many up until the middle of the last century. Here's a synoptic chart for the region of Australia and New Zealand for 1934, surface chart, observations basically confined to the coastal populated regions. Tasman Sea, neighboring Pacific and Indian Ocean, virtually no observations whatsoever. And that was true for a great deal of the rest of the globe as well. Every point here, now I'm looking at the data that was available in one day a few months ago. Every data point that you see there represents something between 10 and 100 observations. What you're seeing are the typical standard meteorological data. And if you look particularly at aircraft data, you see that void in the Tasman Sea and the Pacific for New Zealand and Australia has had a substantial upgrade. But then from the mid-19 or late 1960s onwards, we had the development of dedicated weather satellites. And the amount of data that became available was incredible. So we go from a montage in 1965 with 2 visible channels to 16 visible channels with a GOES satellite launched in 2017. And if you think of not only the visible channels, this is what's available in the infrared, water vapor, ozone. This is now just for one day. And we have to remember then that as well as gathering that observations, we really have a challenge. We have the challenge of processing and assimilating that data, all 40 million daily observations, and processing and assimilating it quasi-instantaneously. That is a huge challenge. And to do that, we need computer power. Computational power shown as a development in time. If you look at the red line there, the 2 points to be made is that the CDCs, the IBMs, the CDCs, and the Cray machines that you look there on the peak product computers were, once they came into operation, the workhorses of the meteorological service. So you could argue that meteorology has benefited immensely from the advances in technology. But you could equally argue that meteorology has spurred those advances. Meteorology or National Weather Services were the first customers for all of those machines, and the people programming them were the first people to program those machines. So it works both ways. If I turn to prediction, first, numerical weather prediction as we understand it today, carried out at when IUGG was formed by L.F. Richardson, was a catastrophic failure. He made a prediction for 6 hours for 1 point in central Germany and was wrong by 2 orders of magnitude. Heroic, brilliant, but wrong. And that has implications for the perception of the science, as we can see. If we look at what things are like today, this is the ECMWF skill in terms of an anomaly correlation as a function of time for the day 3, 5, 7, and 10-day forecasts. And the difference between the 2 lines for each forecast is the northern and southern hemisphere. And you can see that up until about 2003, there was a marked difference between the hemispheres. That decreased with time, partly because more observations became available, satellite observations, but more noticeably because scientists got cleverer and figured out how to assimilate the data into numerical models more effectively. And that, from 2003, is what you see there, is that improvement and understanding. But along with that, and if you recognize that now we're producing forecasts, let's say, for day 6 that are as good as the day 3 forecasts in the past, that means you're now getting, for large-scale events, 6-day warning of an event likely to happen. Whereas before in 1980, that was a 3-day warning. So now you have a 6-day horizon, and after 3 days it's been confirmed to you, and now you can take action. That in itself was a revolution, but here's another revolution. From around 1989, meteorologists acknowledged that they would never have a perfect initial state, and therefore they figured out how to assess how bad their forecasts might be because their initial states were not perfect. This is a complete turnaround in terms of, instead of getting better and better forecasts, you say, can I get the worst possible forecast that's consistent with the data? And by doing that, you have a probability distribution function. Can I move you on and look at complexity? Just one diagram here. And this is really simply the global scale coupled climate model. Starting in the mid-1950s as very crude atmospheric models, they've accrued with time elements of all the associations represented here this morning. The hydrologists are on board, the cryosphere people are on board, the oceanographers are on board, and all of them have had to learn a common language so that they can operate with the same tool. So there's a case to be made for saying that these models have been an unifying effect across much of IUGG science. Now I turn to the question of perception. Is the discipline genuinely a science? You say, what a stupid question. But for a century, the atmospheric sciences have had to battle with this question. So let me run through with you what happened. we were beset by the fact that astronomers could make brilliant predictions and we couldn't. And the implication of that was the leading astronomer in the world simply declared meteorology is not a science. Even one of our own said, unless we can make perfect predictions, we're not a science. But back in the background there was this little mathematician in Paris saying, maybe it's impossible. In the 1950s, the recognition that meteorology and atmospheric science was important, but basically it was sterile and underdeveloped. If I can take the example of the US National Academy of Science in 1955, appointing a commission for atmospheric science and forcing onto that as a member a leading physicist just to indicate that they wanted the commission to look as if it was real science. That persisted through the 70s and through to the late 80s. Here's a Nobel Prize winner reflecting on that time and saying, I never got invited to a chemistry department. The kind of chemistry that I was doing was looked down upon, frowned. Or the doyen of the historians of science saying, basically, unlike physics, chemistry, biology, and geology, meteorology doesn't have a sound theoretical framework. He's wrong, but he's the doyen of historians. And then if I can move on, and simply in passing, the leading philosopher of the science at that time actually saying, clouds are my picture of what an unpredictable system is. What was the change? Two things. Lorenz basically said, if you have a deterministic system, then so that the future depends upon the present state, then an approximation of the present state does not in any way approximately define the future. This was a revolution. The second revolution was simply Rowland and Molina pointing out that photodissociation of CFCs would mean release of chlorine atoms, which would mean destroying the ozone layer. Both had huge implications, working through to the Montreal Protocol and changing the nature of science. The Nobel Prize presentation for Crutzen, Rowland, and Molina simply said, not only had these people been doing high-level science, but they were saving mankind at the same time. The citation when Lorenz got his Kyoto Prize was basically saying this was the most dramatic change in mankind's view of nature since Sir Isaac Newton. So a science that was hardly regarded as such now becomes something that is center stage. And the aftermath, what you find is that mathematicians have to apologize for misleading the public for 100 years. Even the art reductionist, the Nobel Prize winner Steve Weinberg, has to say that in a sense, yes, you do need different kind of explanations at different levels. And since ICSU has now become ISC, I leave the final word on this to Collins, a leading sociologist of science, saying we basically need to figure out what science is. Let me move on and now talk about characteristics of IAMAS contributions, and I'll focus on three examples. First, the saga of stratospheric ozone on the one hand, and what IAMAS did on the other hand. Three strands came together: chemistry in the stratosphere, James Lovelock, who was born the same year as the IUGG, measuring on the west coast of Ireland and on a ship journey to Antarctic the prevalence of CFCs, detection of the ozone hole, and very shortly afterwards, Montreal Protocol. That, in a nutshell, is how science perhaps could operate. Theoretical laboratory work leading directly through observations to action when there are challenges. What, in fact, did IAMAS do? The ozone community was an exotic animal back in the 1920s, as was ozone itself. It was a subcomponent of the International Radiation Commission, but these guys were determined. They were a mafia, and they set up their own quadriennial ozone symposium, which has existed ever since, producing thousands of papers. Then they made a proposal to become a commission. Just before the outbreak of the Second World War, finally in 1948, they became their own commission. Then IAMAS and IUGG gave them more prestige by electing a leading scientist, a leading ozone specialist, to be successively president of IAMAS and IUGG. And that in itself was tremendous, but the president Ramanathan made suggestions regarding the IGY year, which were going to have profound influences. And if you had turned up at one of these quadriennial ozone symposia in 1983, you would have been presented with these two diagrams by a young Japanese scientist, showing in a public scientific forum for the first time the ozone hole. Dramatic fall off in September, October, before a recovery shortly thereafter. How were those measurements made? Well, the network of ozone sondes that had been amplified at Ramanathan's suggestion, some of them continued thereafter, and this was one of them. So IGY led in effect to this detection as well. Can I move very quickly to something else? That was an example of the association nurturing something. Has the association, has the association actually developed something itself? Well, I would suggest that this PV perspective, potential vorticity perspective, is one such thing where the association has led the way. It's a means of displaying, diagnosing, understanding atmospheric flow on the large scale. And if you look at developments over a period of successive periods of 12 hours, you see that there are coherent structures, and by the end of the period, down in the bottom right there, you see two vortex-like features, which with just 3 minutes of experience of looking at that, you might be able to foretell, and those three vortices there are actually spawning cyclones at the ground. So this is a very powerful tool. The point I want to make is, here's a picture compiled by our chairman this morning of IAMAS presidents. Here are the people who led the way in developing that perspective, along with a few others, I should say. And they all made iconic developments, contributions to that. I won't go through them now, but Napier-Shaw, Ramanathan, Rossby, Obukhov, Sutcliffe, and Brian Hoskins all made direct contributions, seminal contributions to that development. Third project, Global Atmospheric Research Program. 15-year joint ISC WMO program. What did it do? Produced field experiments. In GATE, 40 ships, 14 aircraft in the tropical Atlantic. It produced global plans for global numerical weather experiments. It produced ground-producing study conferences, groundbreaking study conferences, which paved the way to a lot of other activities later on. And it basically educated a generation of atmospheric science with its publications. It had enormous impact, as you can see there. It transformed a whole set of processes, laid the basis for the World Climate Research Program, set the groundwork for the IPCC, transformed the science itself. What was the role of IAMAS and the International Science Council in that? I would suggest to say that it was seminal and it was central at 3 stages. First of all, in the conception. Conception is often a matter of vision, and that clearly was IAMAS and COSPA scientists working in the background, led to 2 UN resolutions. One, WMO was the lead agency. Within a year, there was another resolution where ICSA was going to be the lead agency. What happened in between? Scientists stood firm and said, this is a research program. We must maintain that. In the incubation period, we now had to develop a way of doing things. At that stage, IAMAS resolved to say, this is atmospheric research and it must be remain so. Secretary General of IAMAS at that time, Warren Godson, was firm. And then in that incubation period, 2 conferences paved the way for sharpening the outlook of that vision. And finally at the birth, if you had been in the IUGG assembly in Switzerland in 1967, you would have been amazed, because from September to October, a resolution was adopted by IAMAS, IUGG, the International Council for Science, and finally the WMO. It all came into being within 3 months. It was a masterful exercise with the president of IAMAS playing a salient role, because when there were objections from WMO people about how lacking in operational focus the program was, the then president of IAMAS said, This is the way science is done. Finishing now, we've done two things, if you like. We've educated, nurtured the discipline itself by focusing on science, but also if you read Sutcliffe's quote, and Sutcliffe was the president during that crucial period that I mentioned later on, IAMAS has been able to sustain the fact that this discipline has intrinsic value as well as practical significance, and take those two along. So I hope I've given you enough to persuade you that IAMAS has fulfilled its mandate and is continuing to do so right now. Thank you, Hans.
Hugh, that was a wonderful talk. It's actually sort of two elucidations on your points. I mean, a lot of what drove the fastest computers was actually nuclear weapons programs. But having been at Livermore Lab, let me say that you don't get to test the new computers with classified programs as the people are developing it. And so the very first programs that would go on were actually models of the global atmosphere that Chuck Leith put together and ran as tests. And so his models became the tests for these machines before they were turned over to the classified community.
Yeah. I don't want to underplay the role of politics and warfare.
No,
in
no,
our discipline.
I'm
That's
just saying that
clearly the
it
case.
actually was atmospheric models, generally the first on the thing. The other on the perception issue, just sort of a nuance, that a lot of the early prediction people thought about was sort of empirical and drawn from clouds and things. And then in the 19th and early 20th century, there came this effort to get numerical observations and have them and put them on maps, and then Richardson's effort, which sort of failed. And then, as you said, satellites came along. The trouble with early satellites was they were mostly visual things about cloud systems that took you back to the empirical way of doing it. And so it's sort of, there was sort of a split in the science community as the forecasters went back to sort of using their old techniques based on things. And before, satellites ultimately came so they could give quantitative measurements in the of quantities in the atmosphere, which has been a real advance and stuff.
Thank you for these comments, Mike, but I think thanks a lot for this very tour de force which we have just seen, but in the interest of time we will